Today we're going to jump into continuity. Continuity is not a new topic. You were actually all kind of like playing footsie with it on Monday, right? You were kind of just barely there. You all started to kind of see that there were times when limits are what we actually get, right? And there are other times where what we have for a limit did not match what we actually get. We're just going to try to pin that down with some language today to help make it a little bit more steadfast. So let's start off with just a little quote. We've got mere change is not growth. Growth is the synthesis of change and continuity. And where there is no continuity, there is no growth. Before we get too much into the math, not that what we're about to do is not math, if I was just going to ask you from an out of this classroom context, like if I said continuity to you out on the street, like what would you think? What does continuity mean? What does it sound like? Yeah. Continuation, continuous. Tell me what continuous means. Let's use some like our language, right? What do you think?
What's the word? The continuing of expectation.
So try to do it without continuing in it. Give me a shot. Go ahead.
That it stays the same, but then kind of doesn't end.
No ending. I like that doesn't end. I like that one probably the best. Do we all feel pretty good with like no interruption? Continuous means no interruption. That one's really, really nice. Did anybody else have other ideas? Go ahead.
Well, I was just going to say to progress without interruption.
To progress, I like the progress idea as opposed to staying steady. The reason I'm a little worried about like the staying steady is in math terms, we have that as a word looks like constant. And I want to talk about graphs that maybe do have a little bit of up and down to them. But I'm just talking about like, I like that idea of that interruption. That's really what we're trying to get at, is that there isn't a break, that there isn't an interruption, and that I am able to kind of metaphorically talk about this as a continuous uninterrupted story, right? So let's just take a look at some graphs. Let's just get some opinions on these. What do you all see as the graph that does not belong? Yeah, go ahead.
Top right one.
Top right one does not belong. Tell me why this stands out.
Because all the other ones have like limits or asymptotes.
They all have asymptotes, so this is the one without an asymptote. Okay, I like that. Did anybody else see it for another reason? Go ahead.
Yeah, there's break off.
They kind of have that break. Do we all see that like the other ones, because of the asymptotes, have an interruption, right? We can loosely see this as the ability to draw these pictures without picking up our pencil, right? So we've got this ability here. I can kind of draw this one without picking up my pencil. I can sketch along it. For all the others, if I tried to sketch this graph, I would have to pick up my pencil before I was able to continue on. That's a nice way of being able to recognize that we have some interruptions. As we'll recognize, there are other times besides asymptotes that we also have interruptions. And so we're just going to group all of those together as saying that those are not continuous because they have an interruption. Okay. So let's take a look at some graphs, because again, we are in the process now of trying to formalize limits, which means we are trying to break our definition. Let's remind ourselves again, what's the definition of limit? Who can give me some context for the discussion? Let's go ahead. Yeah.
The trend of the function as it approaches infinity.
I like the idea of it being an approach. It doesn't have to approach infinity. Remember, there have been times where we've come closer and closer to 1, like with 0.9 repeating. So it does. I do like the idea of approach. At the moment, that sounds more like an algebra topic, right? When we're talking about like plugging in X and looking directly above it. In that conversation, there's no approach, and it gives me just that algebra. And that's really the difference that I want to kind of stress in these lectures, is that if we're talking about what is, that's a perfectly fine discussion. That's an algebra discussion. If I say, what did I expect as I approach, that's a limit. So limits, if you want a nice, simple, cohesive story for limits, they are the logic of approach. So if you don't have that written down, I'd write that down, right? Limits are the logic of approach. If you are tackling a limit problem and you have not considered the approach, then you're not doing a limit problem. You're doing something else. So you've got to make sure that it is that logic of approach. Now, what we're going to find is that sometimes that approach does not match what we actually get. That's totally okay. It's okay that sometimes our expectations and the things that we approach are not what is actually there. It just means that we need to kind of call that out with some language. So let's take a look here. If I'm going to look at this graph, this one can look a little intimidating, but as a reminder, we all have the ability to graph anything just by plugging in numbers and plotting points. So let's come off to the side here. Draw a little coordinate plane. And let's just try some values. If I say x equals 5, absolute value of 5 is 5 divided by 5 then would be 1. So above 5, I have a height of 1. That's great. What about 3? Absolute value of 3 is above 3, divided by 3 would be 1. Very good. And then if I've got a half, the entire answer is going to be 1. And then if I put in a small decimal, it's going to be 1. And if I have 0 divided by itself, it's going to be, good job. Very nice, right? We break a trend there. There's not the ability to get a height that corresponds with plugging in 0. So that's fine. We'll just put a little hole there then. No problem. Everything else, though, we got some nice good answers. Let's do some negatives, shall we? Let's do some negatives. So now I'm going to plug in -5. Absolute value of -5 would be divided by -5 would be -1, right? Positive divided by negative. So I get -1. What about -3? -3 absolute value would be positive 3 divided by -3 would be -1. And then if I continue that trend on in, I'm going to get -1 and -1, -1 until I plug in 0 and I get undefined. Very nice. So even if we don't know what these graphs are going to be, we can always just graph them, right? We can always just consider. Now, this is the graph. If I want to actually consider the logic of approach as I get closer and closer to 0, then I need to go through the storyline of considering the approach. We don't just look at, we look at approach. So now if I go through and I say, let's look at the approach. Well, we have two directions of approach. We need to look at the approach. We could go from the left and the approach from the right. So let's start to put that down so we share it with our audience. X approaches 0 from the right would be a superscript plus or minus? Plus from the more positive, right? So we could say absolute value of x divided by x, that limit. Well, if I look at that, then I have a height of 1, 1, 1, 1, 1, 1, 1. And no matter my approach, no matter the data I collect, as I come on in, I expect it to be 1. That's great. Let's look at it from the other direction. As I come from the negative, then I've got data that I need to collect, trends I need to consider, and I need to look into that story. So I've got -1, -1, -1, -1. And if I bring myself in through any path and I consider any data along that approach, I expect it is going to be -1. Now the limit asks me for a single value that I approach. What do I approach? It does not exist. There's no single value I approach. So in this situation, we say that the limit does not exist. So we've dealt with times where the limits don't exist. That's totally fine. It's just a reminder that we do have to go through it as a story, though. We have to go through it as a story. Because did this have anything to do with a divide by 0 error? In this conversation, never came up, right? I used it only to draw a graph, but I didn't use it at a single point in here. I did not say because it's a divide by 0 error, the limit does not exist. That would be a completely mismatched discussion of saying, I had a problem, so along the way, I had no idea. No, that, right? We want to make it along the way, it suggested and I confirmed, so the limit is. That's the kind of conversation you want to outline. Yeah, go ahead.
Isn't 0 over 0 divided by 0?
It is, but in this conversation, I never tried to plug in 0. I asked, what did I approach from the directions? And it's because I approached two different things that the limit didn't exist. It had nothing to do with 0 in any of the ink I put down on the paper. Now, if you said, what is f of 0? That would also be undefined. That's fine. But this didn't ask, what do I get? This asked, what did I think I was going to get? Right? What did I approach? So we just want to really separate that those are two different questions, although they do have some overlap. Okay, so let's take a look. We've now got this graph. We've got some data. Even without giving you the formal definition, if I was going to ask you, is this continuous, what would you say?
No.
It's got an interruption, right? A pretty nice interruption, right? Is it an asymptote? No, but that would have been another interruption, right? Is it a hole? Be careful. Holes are just where I have a certain point that is missing and I've removed that. This technically has maybe 2 holes, but really the big thing in the way is the fact that it has a step discontinuity. Like it has a step. It kind of took me from one thing to another thing immediately. So I've got an interruption that can occur whenever I have 2 heights that are just not visually connected. So we could say that if the limit doesn't exist, then I must have an interruption. Does that work? Let's try that. Limit means I have to approach. And if I approach in from here, and I approach in from here, and I get different things, would it make sense that they would have to be disconnected? Yeah, that feels pretty good, right? Even if as they approached an asymptote, that would have to be a disconnect. What if I had a graph off to the side that had a hole? Would this one have a limit? Yes, it would. So I'm not saying that if we have limits, we're good to go, but I am saying that limits seem to be a part of the discussion. That if the limit's not there, that implies I have been interrupted. So limits are a piece of saying I'm continuous, is that I need to have this kind of idea of getting closer, right? This ability of being able to drag my pencil along. Okay. So we can write down a little bit of an insight. If the limit does not exist, then f of x is not continuous. This is good. This is a good break, right? This is a good, like we were able to break kind of the things that we were taking for granted. Let's go look for some more. Let's look for some other interruptions. Here are a bunch of different interruptions. Let's explore these and figure out if they are continuous. And if they're not, let's just figure out why. So like I look at this one here, this one is a line with a hole in it. Is this one continuous? Let's try it. Let's try drawing it without picking up our pencil, shall we? I'm going to draw this without picking up my pencil. Even if you want to get real clever on your end and be like, oh, I can draw a little circle here. Like you're going to like try to overlap it and double overlap it to like show me you could do it with your pencil. Like there's nothing there, right? There's nothing there. If I was going to draw this, there's a gap. I would have to jump over the gap and then continue the graph. So this one does have an interruption. This would not be continuous. But I know this one has a limit. I would have expected the same thing if I was looking at stair-stepping on the way in and stair-stepping on the way over. So why does this thing have a limit, but it's not continuous? Go ahead.
The limit of x doesn't equal f of x.
Ah, so it's a matter of saying that there's nothing there, right? Like just simply put, there's nothing there. So you can't draw it. So you have been interrupted, right? So we've got a certain piece of saying not there means not continuous. So now we had on the last slide, if I don't have a limit, if I don't have the ability to approach, that's going to make an interruption. If I don't have the ability to put something there, that's going to be an interruption. Okay, that's feeling pretty good. We're finding some breaks. Let's look at the next one here. Now I'm going to fill in that gap, right? Now you can't say there's nothing above x equals 2. I've made there be something above x equals 2. There's a point there now. Can we draw this without picking up our pencil? Is it continuous? Oh, a little bit more enthusiasm, y'all. Is it continuous? No. Why?
Still have to deal with that hole.
So we still have this hole, but like now we want to start making this a little bit more formal. I don't want to say because there's a hole that I see with my eyes, because then all of a sudden I have to start wearing your eyes. And I want to say that it's discontinuous because I have to pick up my pencil, because then I've got to make sure I always carry around a pencil. And if I don't carry around a pencil, I will never be able to know if things are actually discontinuous, because I'll have to use a pencil. Pens are not allowed because your definition said pencil. You say, no, any writing implement. And I'll be like, well, then I must always draw. Like, we didn't have to draw here. We just looked. So like, what are we seeing? What are we capturing? Build on that.
I'd say, because the limit as, x approaches 2 does not equal, f of 2.
So let's check that from a story standpoint. I'm going to drag my pen across this. And in so doing, I'm suggesting that the limit is going to be this, right? Kind of got that height as I'm stair-stepping my way on up. And from the other direction, I've got a similar limit. So the limit definitely exists. And I do have a value. They just don't match. Okay, so now we've got kind of like that third condition. So now it's not a matter of saying it's not there. It's saying even if there is no match for f of 2, what I get as a height above 2, and what I expected as I approached 2. You see how we're starting to describe more formally this ability of being able to draw without picking up our pencil? Now it's the ability of like, what does it mean to draw without picking up our pencil? It means, oh, I must be able to approach. And it's like, well, what does it mean if it's not interrupted? It means, well, it must approach and then actually be able to draw when it gets there. So those are our two pieces that we're starting to see. Oh, I've got this ability of approach. I've got this ability of being able to draw when I get there. And I have this ability to be able to go away afterwards. Let's look at this next one. Here again, I've got a value above x equals 0. I've got an asymptote that we approach as we get closer and closer. Let's explore both of those details. Let's explore the limit. The limit as x approaches 0 of this function would be what? Remember, we want to make it like that stair stepping, right? Like we're looking at heights along the way and collecting data along our journey. So we've got height, 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 height. What's the height we're approaching? We could say infinity. Some books do say infinity, but I'm really trying to do my best to make it so that you never have to write equals infinity ever. Because does it make sense that I reach a forever height? Like, what is that height? Did you all get there to double check? Right? Is there actually a height that's at the top of this? No, there's no top. So I like to say that, yeah, either like the limit does not exist because there obviously is no limit. This thing's blowing the ceiling off the paper, right? And if we wanted to say why, we say it's because it's blowing the ceiling off the paper. It's growing without bounds. So the limit here does not exist. And if I said, what did I actually get at f of 0? What's the height directly above 0? The height is 1. There's a point there. It says so right here. So it looks like we're starting to support that idea of I had an interruption because what I approached did not match what I got. Okay, let's take a look at this last one here. We've got a bunch of different discontinuities. We can choose any of them along the way. Let's look at maybe above x equals 2 again. So we've got the limit is looking at the heights along one approach compared to the heights along another approach. And so does the limit exist? No. So are we going to have an interruption? Yeah, absolutely. Before we even look at what I actually got there, I have to have an interruption because my pencil has magically teleported from drawing at one height to drawing at another. That means it has been interrupted. So I think we've got enough to kind of formally lay this down. Continuity is going to be when I approach something and get it. Does anybody have any questions about where I'm pulling that from the situations we've explored? Okay. So this is important because like now that we kind of had that loose language, I always try to give you all a good foothold by which to start the conversation, but I always want us to make sure that we understand that this is still a math class and not a class of anecdotes, right? I'm giving you those anecdotes so that we can start the conversation from a good place, that you feel like you are involved with it. If any of you on your quiz say the limit doesn't exist because I had to pick up my pencil, you will not get full credit. Because that means that to confirm your answer, I will need to find you and I will need to hold your pencil, right? Because you said that it relies on your pencil and I need to find your pencil. Like we don't want to have a discussion about pencils, right? Pencils are not the key here. The insight and the logic is the key. We want to make this come from a place of logic. So let's see if we can capture this in a cohesive way. So here's the formal definition. This is the formal definition. If I ask what does continuity mean, it means this. No pencils. Pencils are nowhere in this definition. But we can always use that as a way of understanding that continuity, specifically above a certain x value, we could call that A, That continuity means that the limit as I get close to A is exactly what I have as the actual value. In other words, what my pencil approaches is what it draws, and then it continues to draw more things directly afterwards in a non-interrupted fashion. Notice, by the way, that this also helps us pin down some of the questions at the very beginning, right? Like if we scroll all the way back to the beginning for the warm-up, I was discontinuous here. How come? Because the limit did not exist, right? The limit from one direction did not match the limit from the other direction, which meant that the limit did not exist. Oh, we would need to write that in our language the same way that we wrote this one, right? We would need to show our audience that I looked at it from one direction, I looked at it from the other direction, they did not match, therefore the limit did not exist. You could even write a little sentence. You could write something like, the limit, notice I didn't write lim, right? Lim does not mean limit. Lim means I'm considering the list of data along the approach. So I could say limit does not exist because the limit as x approaches 0 from the positive did not equal the limit as x approaches 0 from the negative. Oh no, that's not right because lim doesn't mean limit. What am I missing here? I need the function note, like I need to say, what did you consider the data from? So you need to write what you were looking at. Just small little details, but I want to save you all kind of like those partial points. If you say lim means consider the data you were getting along the list. And if I say of what, you say, I didn't write it, then I don't know exactly what you're talking about. Small detail, but still a detail, an important detail. What about here? Somebody else, tell me why we had a break there. Good.
The limit of f(6) does not equal function of 6.
Very close, except we would want to write that not as the limit of f of 6, but the limit as x gets close to 6 of f of x. Because by leaving it not as a 6 on the inside, that gives me the ability to put other numbers that are close to it in there and grab those as data. And we could say that's exactly right. This limit did not equal what we actually had. Very nice. Right, small details, but they're details that are prevalent and they hit people on quizzes and tests. So if you all think that you might be at risk of these, like write yourself notes, right? That's a good way of being able to prep yourself when you come back from spring. What about this one on the far left? Who can capture that one? Right, we want to say that there's an interruption Y. There's two pieces we got to look for, right? The two pieces are limits and what we actually get. Where does the breakdown occur? I'm going to throw it to somebody else. Appreciate y'all. Yeah, go ahead.
Would be the limit of f of x as you approach -4 does not equal f of x of -4. So you're approaching from when you approach -4, you approach 2, but you do not actually ever hit 2.
Because 2 does not equal, what'd you get when you plugged in -4?
A blank, yeah.
A blank. What would we write for that?
Doesn't exist.
Does not exist. Does that all make sense to everybody that 2 is not the same thing as does not exist? Great. Then that's a great way of being able to write down your answer, right? I looked at the limit was 2. I looked at the value didn't exist. 2 is not the same thing as doesn't exist. So I must have been interrupted somewhere. Like, that's great. Excellent. Good. Yeah.
Would you write it because f of -4 does not exist?
Totally fine. It's just we would want to tie that into the continuity discussion somehow. So you'd want to say like, because it does not exist, right, then it violates the definition because does not exist could not equal the limit, right? We just want to tie it back to that definition as strongly and securely as possible. It helps better than writing down like, I considered how it approached, and I've got to be like, how? And you're like, I looked at this data, and I'm like, but did you look at all data, right? Like we try to find a way to avoid having an argument with anybody who disagrees with us through our paper. So let's do an example. an example here. We've got a piecewise function. Piecewise function means that I am transitioning from one graph to another graph, one function to another function. So I have an opportunity to be interrupted. I have an opportunity for a disconnect. So we could ask whether or not this is discontinuous at 1. As a reminder, we read these by saying, if I am any x value not 1, then I am talking about this function. If I am an x value of 1, then I'm talking about this function. In other words, I am the top thing almost always, unless x equals 1, then I get the height from the bottom descriptor. So we could ask ourselves, is this continuous at 1? Well, before we start going into like the stories and narratives, now that we have something formal, something true to land on, like let's use it. We know continuity means that the limit as x approaches 1 of f of x has to equal what I actually get. So the question is that true? Well, let's do maybe the easy parts first. If I plug in 1, f of 1 will be what? 1/2. So I can write off to the side, I can say f of 1 equals 1/2. Great. Then I can consider the limit. How do I formally consider limits? But
From the approach.
we've got to consider it from the approach. Do we want to do that with data? Data is going to be limited, right? That just means you chose the data, and your data suggested. How do we do the approach? Let's start with that. With what? On the graph? How? We don't have a graph. I don't want to draw a graph. Do you all want to graph that? You could. Okay, go ahead. Be a little bit rough. What? What do you got?
Well, I'd consider like really small values are really small.
We could do really small values, but are your values small enough?
But what I'm saying is like, it's that thing where you do like x squared over x squared and then x over x squared to like find what the limit is, you know?
Oh, you're saying that we could like maybe kind of scale them down in terms of each other? Like we could find that biggest driver? That worked really well when I had things running off towards infinity. Here I've got things running off towards 1. First, do I get to just plug it in? That'd be a completely wrong discussion, right? Like that'd be saying I'm considering the approach by saying it is. That's not excellent. I could plug in data, but anytime I plug in data, then that's really going to leave the argument saying that I chose just data that supported my answer. What we really want to remember is that to solve a limit formally, we need to consider the approach from 2 directions. From 2 directions. So let's make sure we write that down. We need to show our audience that I considered the approach from 2 different directions, from a little below and from a little above. Well, if I am a little bit below, where am I grabbing data from? Which part of the piecewise, top or bottom? The top part. So I know that along this storyline, with values a little bit less than 1, I'm grabbing it from this. Whether I try it with some data or I do it with some algebraic manipulations, we might recognize that our answers correspond with something a lot simpler. They correspond with, well, the top is x minus 1. Can I write the bottom as x plus 1, x minus 1? Do we feel good on that? Can I factor it out that way? So now that I have it in this structure, let's not try specific values, but let's imagine the specific values, right? Let's imagine that I did plug in like 2. Then that means I have 2 minus 1 on the top and I have 2 minus 1 on the bottom. What's going to happen to those results? They're going to cancel, right? And if I plug in 1.5 minus 1 over 1.5 minus 1, are those going to cancel? In fact, what's the only value that's not going to cancel when I divide it by itself?
0.
0 would not work. Am I at risk of that along the approach? Along the approach, I'm never at 1, am I? I'm always getting closer. I'm always collecting data nearby. I have no divide by zero possibility because I never reach the thing that could give me trouble. Well, that means that I can get the same data from that, right? Because every data that I would have collected would have simplified out from those other parentheses. Well, this one here, if I graph it, has absolutely no interruption at plugging in 1. In other words, this thing that I have created is another equation that gets me the same data and has no interruption at the end. In other words, now that I've found this new, nicer way to collect data, sure, now we can recognize that this thing is able to be evaluated as plugging in 1. No interruption. Do y'all see how I used everything you were talking about, everything in terms of data, everything in terms of graphs, everything in terms of approach, but I never allowed myself to replace a variable. And in so doing, I was able to think of everything it could be. In fact, if we did it from the other direction, if I looked from it being a little bit above, I still would have used that top part of the piecewise function, right, for data collection. And if I'm a little bit above and I was plugging in things a little bit more than 1, it still would have simplified through those parentheses in the exact same way. So in fact, this exact same logic works right there as well. It's just that this is for values a little bit bigger. So on your paper, will you have to write this twice? Yeah, you will, right? Because I've got to show that this came from one direction and from the other direction. However, now that I have shown that from one direction it approached 1/2 and from the other direction it approached 1/2, the limit is 1/2 and the actual value is 1/2. So the way that we write this now to our audience is we say f of x is continuous because the limit as x approaches 1 of f of x equaled 1/2, which equaled f of 1. Oh, and this was because the limits from both directions equaled 1/2. Oh, so I could write that all in one line because the limits as x approached 1 from a little bit less equals the limit as x approaches 1 from a little bit more, which meant that I have an overall limit that also equaled what I got. So this thing is continuous. This is how we solve those problems, right? If I'm saying the limit has to match what I get, you have to check all parts of the limit and what you get to show they match.